So now at this point, we have the error message which involves the transform. And as I said before, that's because we're using these expressions right here, which isn't compatible with a compile block right now. That could change in the future, just so you know, but for right now, this is not compatible. And the other thing to keep in mind is if you want to see what all these limitations are, you can find that in the help docs. And so we'll go ahead and just go to the help docs. It's easiest to bring it up and just type in compiled. And there's a little article that's been written up specifically on compile blocks in the user guide. So it's not the actual geometry node help. It's this user guide section right here. And if we go down, we have the restrictions that tell us, in this case, no local variables, no per component expressions, which includes this right here. Now, I'm not going to go over each one of these rules, but just so you know, if something's not working, it's worth checking this out to see what may or may not be compatible at the time. Right now, though, what I can tell you is that we need to get rid of this, and also we need to have the extract centroid SOP to extract a centroid that can be used for this transform. We need to create a spare parameter for this transform. So in other words, I need to use the point function just like we did down here in this point wrangle to find the information on this extract transform. So just like the point wrangle, we need to have this extra input right here hook up to the extract centroid. And the way that we can do this is by going to the cogwheel and saying add spare inputs like that. And towards the very bottom, we have the spare input. If we drag over the node, we can then see that we have this little purple dashed line connecting to that extract centroid. And that's basically saying that we've connected an input just like we did here on the point wrangle. And now we can actually use that point function to go through the purple wire into the extract centroid to find the information. So now under the pivot transform, for the translate, I'm going to use this point function. So points, for the purple dotted line spare input, you need to go negative in the indices. So instead of saying 1 like we did on the point wrangle, it's going to be -1. We go the other direction when we create these spare inputs. So -1, 0, that's going to be the point number that we're looking for. We're trying to find P, so I'll use the single quotations, P, and the next thing that we can provide is what component of the vector, what index of that vector am I trying to fetch? In other words, in this case, I'm trying to get the X component, so we start at an index of 0, and this will go through that purple wire to find the X position right there. We'll do the same thing, except now change this to 1 so that we have that going in the Y, and then index here of 2 for that position attributes to get the Z components. And now as you can see, we have this populated. And the nice thing is that the way that we have it happening right here is compatible with these compile blocks. So this is the proper way of doing this. And so yeah, there you go. It's just something that you have to know with these compile blocks right now. In the future, you might be able to find an easier way to do it, but for right now, know that this is the proper way of doing so. Okay, so we're almost there. If I try to go ahead and run this whole thing now, we're not going to have a multi-threaded performance. And so if we bring this up and let's say that I go ahead and get rid of this blast, what you'll notice is that even though this is thinking, we're not using our full CPU. So what gives? Well, there's one more thing, well actually two more things I have to teach you about this before we can move on. The first thing here is that the file SOP, even though there's no errors down here, this is not really compatible with multi-threading. And so, in other words, before these blocks begin, we need to be sure that the file SOP itself is outside of this yellow box. And the way that we can do that is by going to the top and creating a block begin node. So this creates basically like another boundary for this whole compiled loop right here. So let me try selecting just that and then going after this file SOP. Now our file SOP is outside of the yellow region. Okay, there's that. And also one thing to keep in mind is that anytime you have a situation like this copy to points where the first inputs is bridging across this orange area into a yellow area, that's not good either. You want to capture everything within this orange area, or in other words, if you have an orange area, you want everything to encompass it with the nodes that are involved. So just like we did here with this begin, we can go up here to this for each begin, copy that, go down here, paste it, and change the method right here to fetch inputs, and set that after this compile block. So now this connectivity also lives in one spot, and we're not taking this wire and spanning across a yellow and an orange section. Okay, so now that we have that, the last step to get this multi-threaded is to go to that for each end and to check on multi-thread when compiled. So now that we have this, let's go ahead and refresh. And if we go to our performance, we're now using the full CPU. And what's great about this is that we're able to work on 35 pieces at the same time. So we're seeing a speed increase of probably about 35 times what you'd see otherwise. And so after that's all done, we now have this as a result, which is pretty awesome. It's really fast to do now. The only thing that's not so great is the smaller pieces are getting fractured really intensely, while these big ones are not. And that's because if we go through each individual piece and we're scattering points, let's say 50 points right now, well, 50 points along a big piece is very different than 50 points along a small piece. So we're going to make a really quick change. Let's set this to manual real fast, and then we'll just go ahead and bypass all of this. And so what I want to do now is, instead of force totaling this count to 50 per piece, say to scatter on the voxels independently. And by doing this, we just go by, let's say, a world scale, and it doesn't matter how many pieces we have, this density is consistent across everything. So now let's say we have a total of, well, how many points is this? About 5,000 points, but as you can see, the distribution is even for small pieces and big pieces alike. So let's try that, a density scale of about 120. And then I'll hook up these for each loops again, and let's see what our final result gives us. And so now by scattering on those voxels independently, as you can see, we have a big piece. There are the fractures. For smaller pieces, that density of points is about the same. Okay, great. Well, in the next video, let's talk about how to activate all these things. We'll then move on to animation, and we'll start incorporating all the other effects.